Okay, so let's kind of talk about what the exponential function looks like. And so here is the basic parent function. Okay, so the way that our exponential growth model looks like is this value b is called a growth factor. Okay, and this growth factor can be one of two things. It's either growth or decay factor. For what we're talking about today, we're going to be dealing with growth factor. Okay, and there's two conditions. If b is greater than 1, this is going to indicate growth model. If b, this base, is less than 1, and again, we'll be talking about absolute values of it, we're going to be talking about a decay model. Okay? So in this one, for today, we're only going to be talking about growth. So the bases of our exponential functions will all be values greater than 1. And the basic generic function for exponential growth looks like the following. It'll have a horizontal asymptote. At y equals 0. So the way that that'll be represented is just a dashed line. An asymptote means that it's an imaginary line that a graph approaches but never actually reaches. So the graph will get closer and closer and closer to this line, but it'll never actually reach it. Okay? When I ask you to identify the horizontal asymptote, the way that you're going to do that is through an equation, y equals whatever that asymptote is. Right, so as your graph, so this is my basic a times b to the x function. Okay, it's going to have an asymptote at y equals 0. The domain and range can be identified as well. The domain of this function will always be all real numbers. The lowest x value is negative infinity. The highest x value is positive infinity. It doesn't matter any kind of manipulation to the function, that domain is always going to stay the same. Now the range might change a little bit, but it's going to be one of two things. The range of this parent function, what would be the lowest y value you have in this graph of this red function? This y value gets closer and closer to what? It gets closer and closer to whatever that horizontal asymptote is. And then the highest value is infinity. Okay, but now it doesn't ever reach this value of 0. So there's going to be a parenthesis here, okay, so that it gets closer to 0 but never actually reaches it. And now the only other possible case for your range for an exponential growth type model is if your graph were reflected across this asymptote. If that's the case, and that happens when a is a negative, and I'll talk about that here in just a second, but if a is a negative value, then your range is going to be negative infinity to 0, or whatever the asymptote happens to be. Okay, so this number right here, the lowest part of your range, is always going to be the asymptote. Okay, and then depending whether the graph opens up and to the right or down and to the right will dictate whether it's 0 to infinity or negative infinity to 0. All right, now, as far as the left and right behavior of the graph, okay, so even though this graph, as we move to the left, this graph is actually getting lower, right? It is falling, but it's not falling without limit, right? It's never going to reach or cross this asymptote. So the way that I'll describe or want you to describe the left-hand behavior of this graph is that it approaches an asymptote. Okay, so if a portion of a graph, whether it rises or falls, but if it gets closer and closer and never crosses an asymptote, that's what you're going to describe the behavior of the left or right side of that. And so here, if we're looking at the right side behavior of this graph, what happens to the right? the graph is getting bigger and bigger. So it's going to rise to the right, okay, or it goes up to the right. Okay. Now again, the left and right behavior could possibly change. Although on the graphs that you're going to see in this section, the left behavior will always approach the asymptote. The right behavior will either rise or fall depending on, again, whether this A value, that multiplier out front, is positive or negative. All right. So what about reflection? Okay, reflection is based on A. So if A is less than 0, meaning if A is a negative number, then the graph is reflected vertically. So you have this vertical reflection, and that will occur across the horizontal asymptote. Okay, so that's reflection. The only way you have reflection if there's a multiplier that's negative in front of your growth factor, in front of your base B. All right, now there's two other things that you may see, and that is vertical shift and horizontal shift. If there's an adding or subtracting that happens outside the function, then you're talking about vertical shift. Okay, meaning if there was a +3 or a +2 or a -6 outside the function, meaning not within this power, then you're going to be looking at shifting up or down, just like with all our other transformations. And then finally, the horizontal shift occurs if there's adding or subtracting done inside the function. So if there's something that's being added or subtracted directly to that x in the power, then you're going to have a horizontal shift. And I'll take a look at all of these here in just a moment. Okay, one last thing regarding this vertical shift. The horizontal asymptote will always be set equal to whatever the vertical shift is. Okay, so if you have a vertical shift of up 3, the horizontal asymptote will be y equals 3. If you have a vertical shift of -2, the horizontal asymptote will be written at y equals -2.